to lecture 24, which will cover autonomous helicopter flight, also last lecture of this semester. We do have a couple of other things left though past this lecture. Your homework 5 was due yesterday, but if you're using late days, and if you still have your entire budget of late days left, then you actually still have till this coming Wednesday, so you have another 6 days if you want to, if you have enough late days left. The other thing that's still in our schedule after today's lecture is final projects. So you should all have a slot for presentation, either a live slot or a video slot. The slots are on Tuesday next week and Wednesday. Beyond that, there's a final project report, which will be due on the 15th, which is a few days after your project presentations. And I think after that, it's all done. At that point, we'll try to get all your grades back to you, give you enough time, a couple of days to do regrade requests if anything seems off in our grading. And then after that, we'll submit grades. But we'll give you a timeline on that on Piazza. Any questions about logistics? Yes? The presentations should be, I believe, but I should double check that it all fits, but I believe it is all 5-minute presentations with 5-minute presentations with 1 minute changeover time. So you should actually have 5 minutes, assuming you can get the other person out of the way and get set up yourself in less than 1 minute. One quick thing actually about the slots. Because we wanted to maximize the amount of presentation time, we'll do the final project presentations on regular time, not Berkeley time. So the first presentation, if the slot says, I don't know, 3 to 5 or something, the first presentation will actually be at 3. If you're the first presenter, be there before 3. So you can actually hook up and get started at 3. I don't know if it's 3 for your slot, but whatever the timing is of the slot. Yes?
Do you have any guidance on how much time we should spend on related work and background stuff versus experiments and results?
Yeah, that's a good question, because 5 minutes is very short. So what I would suggest is spend about maybe one minute on problem framing, including put some citations on slides so it's clear that there is prior work, but you don't have to go into all the details of that work because there's no time for it. But put the citations on there so it's clear you're aware. And then that gives you a couple minutes to explain your approach. And then from there, you have another couple minutes to present experimental findings and conclusions from that. Any other logistical questions? OK, then let's get started for today. So autonomous helicopter flight. It's actually what I worked on for my PhD thesis several years ago now. And this was our team at the time. So on the left, Pieter, our first helicopter pilot. Then Tim Hunter, who was a master's student at Stanford at the time, since did his PhD at Berkeley, now works at Databricks actually. Then Adam Coates, who was initially an undergrad on the project, then a master's student on the project, then a PhD student on the project, has since gone on to be essentially AI director of Baidu Silicon Valley Lab, and from there gone on to, he's leading a lot of things at Apple now. Then Andrew Ng, our advisor, then that's me 10, 12 years ago. Garrett, our helicopter pilot we worked with for the last few years of the project, and then Ben Say, who is one of our early helicopter pilots also, who actually was a graduate from Berkeley, worked in Ron Fearing's lab at Berkeley, but then at the time lived near Stanford, and he was a helicopter hobbyist, and so he was one of our pilots at the time. Most days, though, this was the day all the news agencies came by to see what was happening in the project, and as we were wrapping it up. Most days, not everybody was there. It was just 3 of us, just Adam, me, and then Garrett in the back, slightly occluded here, but very important to save our helicopter whenever our computer control goes wrong. He could take back control and make sure failure in our control did not result necessarily in a crash. So what I thought we'd do today is I'm going to give you, in some sense, two stories. First story is going to be the standard kind of paper story. I'll present to you all the cool things we did and how it all it all works. And then the second version of the story, which we'll do after that, will essentially be all the things we did behind the scenes that don't often make it into a paper, but that actually also made it work. And we'll step through that in our second pass. All right, so why is helicopter control a hard problem? So at the time, essentially, I would say, to kind of position it a little bit, reinforcement learning was not that considered that successful, didn't really work that well. And in general, learning hadn't been that successful in showing much real-world success beyond what people could do otherwise. So Andrew had been going around, actually Andrew had been going around while he was still at Berkeley as a PhD student and asking people, okay, if I want to show to you that I've done something convincing with a real robot where machine learning really made a difference, what would you want to see? What's a hard problem? And from that, talking to a lot of the controls faculty at Berkeley, the conclusion was helicopters are the thing that's hard. If you can do something with a helicopter, then the controls people will be convinced that you actually did something hard, as opposed to, I don't know, maybe a cart pull or something. So Andrew decided we're going to do helicopters. And why was it considered hard? I mean, now, as you might know, we kind of solved it by now. But back then, why was it considered hard? Helicopter dynamics are unstable. Unstable means that if you apply open loop controls, it's guaranteed to kind of just run away from you and not stay in the air. It's not just that it's unstable, because in fact, if you have an unstable linear system, things don't have to be hard at all. You just have a simple linear feedback controller for a linear system, and it'll stabilize it, and you might be good to go. But the dynamics of helicopter are nonlinear, making it much harder to deal with. In fact, they're not just nonlinear, because nonlinear is not necessarily an issue in itself, but they're very complicated nonlinear. In the following sense, when you think about helicopter dynamics, you might look at this helicopter body and be like, okay, that's what I need to model. But really, the complication is that the helicopter interacts with the world by pushing air around. And the effects of pushing air around are very, very complicated. And so that's really what makes the whole dynamics so difficult. Now, in addition to the airflow being complicated, there is coupling. What do I mean with coupling? It means that when you build a system and you have control channels, usually you assign your control channels a certain meaning. And you'd hope that when you apply controls along a certain channel, the intended effect will happen and nothing else will happen. Coupling means that other things start happening too. So how do you control a helicopter? Well, a helicopter has 4 control inputs. So, well, how does it work? I mean, you have blades. The blades spin around and push air down, and the counterforce keeps the helicopter up. Now, you might say, well, how much air do I want to push down? Can I regulate that? Yes, you can. And naively, you might think, I'm going to regulate it by the engine speed. Like the faster it spins, the more air I push down. The slower it spins, the less air I push down. That's kind of true, but the way engines tend to work is that they tend to be pretty good at certain speeds, and they tend to be designed to be good at a certain speed and maybe not so effective at other speeds. So the engine, and it's not easy to spin them up and down. So you're not very reactive if you rely on engine speed going up and down to control this thing. So instead, the way it's controlled is by changing the angle of attack of the blades. As you make the angle of attack steeper, more air gets pushed down, and you get more thrust. And in fact, you can make the angle negative and push air up and descend really, really quickly. So that's one control. That's the collective control. It's how much air you push up, or well, mostly down, but sometimes up. Then what else do you want to do? You kind of want to not just stay up, you want to move somewhere. There's no way for a helicopter to just move forward or sideways. You have no thrusters to do that. What you can do is you can actually reorient your helicopter. The helicopter is facing that way, nose is down. Now that vertical thrust is actually pushing backwards in the earth frame, and you can fly forward. So to fly forward, you first got to put your nose down. How do you put your nose down? There's something called cyclic controls. And there's something called a swash plate on top of the helicopter here. And that swash plate essentially allows you to say, I want a different angle of attack left, right, different angle of attack front back as the blade sweeps through the air. So a little mechanism there that regulates that as you go through the cycle, and you have changing angle of attack throughout the cycle. That will make that you essentially end up exerting a torque on the helicopter that you can make the helicopter tilt forward or backwards, or make it roll left or right, depending on the setting of your roll and pitch cyclic controls. Now, that gives you the ability to stay up, to nose down or up, left, rolling left, right. The last thing you need is the ability to face in the direction you want to face into. That's what a tail rotor gives you. Tail rotor, also you control it by just changing angle of attack, which will affect the amount of air you push, and that way you'll be able to spin left or right. It's actually more to the tail rotor than that. It turns out because you have the main rotor, the engine has a torque, there's a counter torque on the body of the helicopter from that main rotor. And so if you don't have a tail rotor, your helicopter body will actually counterspin to the main rotor. And that makes it very hard to control the helicopter. It's constantly facing in different directions, and this would actually pirouette very, very fast. So the tail rotor's main function is to just stabilize and make sure that you have a counter force for that torque that would otherwise spin you around. But then in addition, slight adjustments in the tail rotor angle of attack will allow you to face different directions. So you have 4 control inputs. A simplified way to think of it is you have vertical thrust in the frame of the helicopter, and you have torque along each of the 3 main axes. But then what happens in terms of coupling? Well, imagine your helicopter is you want to fly forward. So what are you going to do? You're going to put your nose down, and then now you're going to fly forward, you think. What happens next is, well, as you fly forward, blade's going around. The blade is going around on this side, moving forward with your helicopter. It's actually getting more airflow than the blade that's going back. So you actually, even though you did not intend to generate any kind of torque around the body of the helicopter, you actually are, because of the differential airflow between the blade that's going forward, the blade that's going backwards. There are other things in that mechanically, as the blades go around and you have a different angle of attack, it actually doesn't work just like, oh, steeper angle of attack, more air pushed down, so actually now I'm going to go this way. No, actually the way it works is steeper angle of attack, blade goes up a little bit. The swash plate is spring-loaded, and now actually the nose of the helicopter goes up. And so it's actually 90 degrees out of phase. You'll have steeper angle of attack here to then be up here, and the spring-loaded will follow, nose will go up. Now, does it follow exactly 90 degrees? And how do you make sure that's all tuned? Those things you need to configure as you set up your helicopter. Of course, they're not going to be perfectly set up. As that blade is going up and down, there'll be oscillations and so forth. And so there's a lot of coupling between the different things you're trying to do. Then, in addition to the dynamics being complicated, the state estimates are not going to be very precise for a helicopter. You don't have exact position, you don't have exact orientation, you don't have exact velocity, exact angular rate. Instead, you get noisy measurements of some subset of these that you can hopefully fuse in maybe a Kalman filter, a particle filter. Kalman filter is more appropriate probably because it's a unimodal problem, and Kalman filters are very good for unimodal estimation. You fuse that information to hopefully get out a reasonably accurate estimate. Now, when we started working on this, there had already been a bit of success on hovering and forward flight. And here are a few of the works that were happening at the time. A lot of them out of controls groups, some out of Berkeley, some out of MIT, CMU, some universities in Australia. And when you looked at the trend, actually, there was no real trend, except that they were all doing hover and forward flight, but the methods were wildly different. Some people say you need an inner-outer loop PID controller with some hand and automatic tuning. Some people say you need to do, LQR control, H-infinity control, H1. There was all kinds of control methods people applied, and ultimately they all did the same thing. The helicopter was hovering or flying forward, which in itself is actually a hard problem. Because when you think about it, the way helicopter dynamics works, because if you think about maybe an analogy that you would be familiar with, imagine you have just a plate. And you put a perfect sphere, a marble, on this plate. And now maybe there's wind gusts and things that kind of jerk this plate around a little bit. And while you have those wind gusts and things that are jerking you around, including the blades not being perfectly balanced and jerking your helicopter around, you're trying to stabilize that marble on top of that plate. And that's what makes hover so hard. You constantly have perturbations, but you need to then compensate for them in the right way to make sure that marble doesn't roll off. That's extremely similar to controlling a helicopter in hover. And that's why people were saying this is very, very hard. It turned out the most precise hover controller achieved at the time was this one here by Andrew as a PhD student at Berkeley. He had a reinforcement learning approach that was able to stabilize it extremely well. Then he came to Stanford as a professor. He said, let's see what we can do. And here was the first result. This will turn normal colors. This is the first result achieved there after 2 years at Stanford. Shows a helicopter hovering, but hovering upside down. So this is now stabilizing in a more difficult regime than regular hover. Now, a couple of things here. How much harder is this? I would say it's a bit the difference between having a marble on top of your plate that you're trying to balance while you're being jerked around by wind and imbalance in your helicopter and so forth, to now going to a heavy body on top. So it's almost like you put a broom on top of your plate, and now you're being jerked around and you're still making sure you balance that broom at all times. So it's a lot harder. Do note, though, that it's the camera that did the flipping in what we watched here. Right? We did not see the helicopter flip. Now the helicopter was flipped, of course, otherwise it wouldn't be in this configuration, but it was flipped by a pilot. A human pilot flipped the helicopter, put it in a steady state inverted hover, and then the autonomous controller took over. And so when I joined the project, it was right around this time after this had happened, and the question we asked ourselves was, can we do more? Can we autonomously flip it instead of having it pre-flipped? And more generally, can we go to the full flight envelope the way humans can fly these helicopters? And so one of the videos that was very motivating for me at the time is this one here. So RC helicopters are this kind of hobby thing that quite a few people participate in. And some people are known as like the best pilots in the world, and Alan Szabo at the time, probably still now, is known as one of the best pilots in the world for RC helicopters. So let's get a sense of what it means to be one of the best pilots, what happens when such a pilot flies a helicopter. Nothing autonomous here, just to be clear. This is a human pilot, one of the best in the world. You can see it's a lot more dynamic than what we saw in that hover video. There's a lot of upside down happening too. Traveling tick-tock. Essentially, every other second, a new maneuver is happening. There's very little steady state here. Contrast that with the state-of-the-art at the time in autonomous helicopter flight, where essentially the only things that had been achieved was steady-state flight regimes. Hover, inverted hover, and forward flight. And this is just essentially anything this helicopter can physically possibly do, many things you couldn't imagine that this thing could do, it's actually doing no problem. Let me go a little further towards the end here. If you want to look up this video, it's called Sunday at the Lake. He's flying upside down. He can do upside down also. He does it closer to the ground, which makes it more dangerous. If you do anything wrong, you lose it. So this is essentially what we were looking at, and we said, okay, this is definitely a whole different level than anything that's been achieved so far in any of the autonomous control results. So let's see if we can get anywhere near that. That was the goal for our research project. So, next thing we did is said, okay, well, let's try. What do we need to do? Well, clearly we need to find a different trajectory than hover or inverted hover, so we're going to just pick a trajectory, maybe look at this video and say, okay, maybe the helicopter should fly at this trajectory. And then we got to run something to find a controller. So it's okay, well, what can we do to run a controller? Well, maybe what we can do is we run LQR. We have a trajectory, we do LQR regulation around the trajectory, and hopefully we stay on track, and we execute this trajectory, and we're done. I mean, we have our solution, and we have a cool video and our paper, and we're good to go. So that's what we tried. Let's watch this in action. This is autonomous, hovering, flipping. Pretty dynamically flipping, but it's not really staying in place, which it was kind of supposed to do. Then the engine died. Helicopter disappeared. Okay, so a lot of things went wrong here. But let me first clarify what actually happened. So we're flying this helicopter autonomously. We're trying to follow this flipping trajectory. We deviate. What happens next? Our linear sequence of feedback control, our sequence of linear feedback controllers is like not so great anymore for where we are now because we're off the trajectory it is designed for. So it kind of starts doing even worse. And it starts oscillating very big flips around the target trajectory. At some point, it pushes the controls so hard that as the engine's trying to push the blades through, it actually can't. It can't provide the torque. The engine stalls out, and that's it. Engine stalls out, no control anymore over the blades, can't push them around anymore. At that point, well, we lose control. Helicopter drops out of the sky. Now, it actually even dropped, it was kind of tricky, it dropped, looks like it dropped into the trees. But actually the crazy thing that happened is our helicopter pilot, Garrett Doku at the time, he sees, by the way, we told him, look, don't take control back too quickly. We want to really see how all this works. So he's like, okay, I'll have patience. He saw this was going wrong. He's like, they asked me to wait and see what happens. When the engine died, he's like, okay, clearly they lost it. He said, okay, look. He took back control, actually, after the engine died. So after the engine dies, you can still control the angle of attack of the blades. That's electric. So he controlled the angle of attack of the blades. There was still a little bit of inertia in the blades, just a little bit of inertia. It's still spinning just a little bit. He controls the angle of attack in a way that they can start spinning up again. Reorients the helicopter. Helicopter goes behind the trees. It's still on its side. He can't see it anymore, but he knows enough. He just knows so much about how this helicopter works, muscle memory, everything. He actually gets it fully oriented, and it lands on its feet behind the trees. Now, it landed with much too high velocity to fully survive the landing. But kind of, if there had been a person inside in some sense, maybe they would have survived because it landed on its feet and at much lower speed than dropping like a rock out of the sky. Essentially auto-rotated that helicopter into a landing. Auto-rotation is where you essentially engine off and still manage to land your helicopter. The reason he couldn't fully safely land it is because the blades were going so slowly and the helicopter was not high enough up to regain enough blade speed to regain full control. But in principle, you can fully control a helicopter without engine. If you're high enough up, you can get the airflow through the blades to spin up the blades, which again then in turn gives you control over the torque you apply to your helicopter. So very interesting. Our pilot was able to land that and then fix up the helicopter later actually, which was completely crazy that that was even possible after we lost control. Yes?
So these helicopter drivers, like what are pilots, what like state information do they have? Are they just looking at the helicopter?
So there's different setups to pilot these helicopters. Garrett here was just looking at it. He's just standing on the ground, roughly the same viewpoint as the camera, not exactly the same viewpoint. He's just looking at it. He has a remote control, and the remote control allows him to choose who's in control, the computer, so our controller, or he. And at some point when the engine died, he flipped it to him being in control. But yeah, he just watches it all the way as it's moving, and then at some point he decides to take back control. Obviously he couldn't save it, but it's because we told him, let's see if it can actually succeed. Don't take back control this time too soon. There are these days other setups where you put a camera on the helicopter and you then wear goggles and you look through that camera. I don't know if that's any easier. I think probably it's more convenient if you can't see the helicopter anymore, of course, and it might be more fun. But I think if the helicopter is in your line of sight, it's probably easier to do it this way. So we essentially followed all the descriptions what you're supposed to do to control a helicopter, but it didn't really work. So that's a good starting point to do research. Think about what's different about what we did versus what was done before, or wanted to do what was done before. In the past, people looked at hover and stationary flight regimes, restrict attention to a specific flight regime. What you can do is you can collect data in that flight regime, and then you can build a model, even a linear model potentially, and then build a controller around that linear model, and you're good to go and get successful hover, inverted hover, and forward flight. But for aggressive flight maneuvers, there are additional challenges. Namely, it's not even clear what the trajectory should be. The trajectory we chose for the helicopter to follow was actually not flyable. And so, of course, it was going to deviate, and it's not going to succeed then because it's not flyable. Dynamics model, how do you get a good dynamics model when you're in a non-stationary flight regime? Because at that point, it's much more complex to model dynamics of the helicopter than when you're in a single flight regime where a linear approximation is often going to be good enough. So we looked around, and was there any place where somebody had done anything with a helicopter in a non-stationary flight regime? And we found this paper by Eric Ferron's group at MIT showing 3 non-stationary maneuvers. A split S is where you're flying forward, you do a half roll followed by a half loop as a way to change direction without burning your energy to friction. Snap axial roll, which is just you spin around your forward axis, and a stall turn is you're going forward and then you climb and then spin your tail around, come back out. Another way to not burn your energy to friction while being able to change direction. And so the key there seemed to be that they had a lot of expert engineering of the controllers after human pilot demonstrations. They would record human pilot demonstrations, and they would record the angular rate of the helicopter at all times, the velocity of the helicopter at all times, and they would say, okay, since the human pilot had this angular rate, this sequence of angular rates, and this sequence of velocities, we're going to ask our controller to just regulate around the same sequence of angular rates and velocities because they should be flyable, and see what happens. At the same time, there's also a lot of people saying, well, maybe that's not too different from just recording the human pilot's controls and just replaying them. Maybe you can just replay somebody's controls. But nobody really tried that. But after a year or two of work on the helicopter, and the best result we had was this flipping that kind of partially succeeded but then would crash, we said, let's try what we would call Sunday, not at the lake, but Sunday in open loop. So we went out on a Sunday to one of the soccer fields there, and we said, okay, let's see what happens if the only thing, we bring out no instrumentation. It was a helicopter we had never flown before autonomously. We just said, we're going to just record the sequence of controls the pilot applies and essentially have a tape recorder and play it back and see what happens. And that's what we did. So we said, okay, let's just play it back, see what happens. Piloted a forward flight roll. We recorded that. We played back. And then we actually get a forward flight roll. You can see a bit of a dip there. It wasn't like a very high precision thing to do, but it did get the maneuver right. And didn't go crazy. Split S, so a half roll followed by half loop. Stall turn. And so at this point, we're probably a half hour into that day and about 2 years into the research project. But a half hour into this day, we actually have completed 3 aerobatic maneuvers beyond what we were able to do before. We did all the ones that were done before by Ferron's group. We said, okay, what else can we do? We recorded the loop. And we played back the pilot controls, and it did a loop. Then we said, okay, well, let's keep going. Second loop. We can actually do 2 loops in a row. It's still up in the air. We thought about takeoff. Okay, just replay pilot controls to do takeoff. blades spinning up. And there it is, taking off. How about inverted takeoff? We spin up the blades, and we're going to flip it 180 right after takeoff. There we go. And there we were flying upside down. Just, about an hour of effort. There were a few things that didn't work, though. There were definitely limitations. Hover. If you actually want to do sustained hover, it's not going to happen in open loop. It's just drifting away, and it's going to end up completely somewhere else than where you started. Tick-tock, widely considered one of the hardest maneuvers, where you kind of go back and forth like an old-school clock. We're doing the tick-tock, but it's descending very rapidly while it's doing that. It's not able to maintain its altitude. Chaos, which is often considered the hardest maneuver, you spin your tail around as quickly as possible while flipping and rolling. We got the gist of a chaos, but we didn't get any kind of control over where the helicopter was, and it was just moving all over the place. We had to put it very high up to even be able to try this. So in some sense, the lesson learned here was, if you want to just get the gist of a maneuver, and you're high enough up, you can replay controls, and it'll actually get the gist. But if you want any kind of precision while executing those maneuvers, open loop replay is not even going to get close. And when you try to do something continuous like keep flipping, sure, you get flipping. And in fact, I would say the flipping by open loop replay is slightly better than the flipping we had in that previous video, and much simpler. You just replay the pilot controls. But it was still descending over time, and at this point the pilot took control. So lesson learned was that our intuition at the time was, if we can model our controls after the pilot demonstrations, maybe through machine learning to also get feedback into it and so forth, we should be able to do quite well compared to these hand-designed trajectories and controllers. And we should maybe be able to do aggressive maneuvers, not only one, but many in rapid succession, maybe something even close to the Sunday at the Lake video. So the first step was we need a target trajectory. Target trajectories are difficult to specify by hand. Why? Because helicopter dynamics are complex. And so it's hard, and it's not just like a rigid body model that's complex. There's airflow that's very hard to get the right intuition for. Our solution was collect demonstrations of desired maneuvers, because we knew that that would be things that can be flown. But the challenge is that if you get pilot demonstrations, that often not any single demonstration is exactly what you want. So what should you do? Well, collect many demonstrations and then run some kind of probabilistic inference to infer a cleaned up version of those demonstrations. There's two reasons the pilot demonstrations are imperfect. One is that they just don't execute exactly the way they might want to. Two, our sensing is imperfect. And so even if they did a perfect demonstration, the recording we have of that trajectory after running our Kalman filter and so forth is not going to be super precise. And so we want to also smooth that out across multiple demonstrations. So here are our expert demonstrations. And this is for a specific sequence of maneuvers. All these helicopters, now this is the result of the expert demonstrated in real world. We ran our Kalman filter and smoother, and now we're watching the result of the Kalman filter smoother for each of those demonstrations replayed in this graphical interface. And we see they're all doing the same thing. They're doing loops now, but they're not doing it in the same timing, and they're not doing it exactly in the same place. There's definitely variation. So we want to turn this into a single target. How are we going to learn this? Well, what's a natural thing to do here? How do we set up probabilistic inference for this? It's a temporal sequence. So you might want to look at an HMM-like model where we assume there is some hidden sequence we don't know, which is a sequence of states the helicopter actually should be going through. And that should satisfy helicopter dynamics, which you don't know perfectly, but maybe have an approximation for. And then there are demonstrations, which are approximate measurements of what we want the helicopter to do. And then we should be able to just have the measurements, hook it up, run, let's say, an extended Kalman filter and smoother, and get out the hidden state. But the timing isn't aligned for those demos, so we've got to do something extra. How do we align those demos? Well, if you only have two, you can align those two demos. But in practice, we had more like 10 demos. And aligning 10 demos is very hard to do. 10 trajectories alignment is a very computationally expensive problem. What you can do is try to align each one of the demos to a single master trajectory and get alignment that way. And so in some sense, we have a chicken and egg problem here. We don't know the master trajectory yet, but if we knew it, we could align them all to it. And once they're aligned, we can run a common filter smoother to get the estimates for the hidden trajectories. So that's what we did. We said, OK, let's just somehow fill in something. Maybe pick one of the demos, put that in the hidden. Then run something called dynamic time warping or Needleman-Wunsch, which is a dynamic programming algorithm to do sequence alignment. It's used in biology, it's used in speech, and we use it for helicopter trajectory alignment. It's been around for a long time. It gives you the optimal alignment against some cost function that you specify. And then after you've done that, you hide that trajectory because it was just one of the demos. And now you infer through a common filter smoother what it should be. But now the alignment was kind of ad hoc initially, so maybe wasn't the best. So let's get rid of the alignment and realign against our new estimate and repeat till this process reaches a fixed point. Once we do this long enough, usually 5 to 10 iterations, here's what we get. We get all the demonstrations aligned in time, and we get the white helicopter here is the estimate of what the pilot's intent was, what we might want to fly ourselves, which is a cleaned up version of any single one of them. So that's what we're going to want to fly. Let's take a look at a couple of demonstrations. As for double loop here, we did it for the full air show, but let's look at the double loop specifically here. These are demonstrations. After you run the approach I described, the dynamic time warping with common filtering smoothing, here's what comes out. And you can see it's a much cleaned up version. There's no prior in there about needing to be circular or anything. It's just the demonstrations in themselves explain that likely a double circle is what you would have wanted. Look at the purple one. That kink at the top is not likely to have happened in the real world. That's probably just a state estimation error because we maybe had some imprecise measurements at the time. But that all gets cleaned up in this process. So now we have a target. Once we have a target, we need to find a controller to control around that target trajectory. Well, let's take a look at our dynamics models. We would work with the standard dynamics models for helicopters and tune some parameters based on data. And then we'd look at, OK, here's a trajectory our helicopter flew. For every time step, let's look at the predicted acceleration by our model and the actually experienced acceleration by the helicopter. See what the difference is. This is the difference. So vertical axis is acceleration error. 0 is, of course, where you want to be. 10 is 1g. 30 is 3 g's. So you see that throughout this trajectory, at some point, this standard dynamics model is off by 3 g's. 3 times the force of gravity is how much you're off. You might wonder, what does that mean? It all depends on how much control your helicopter has. If your helicopter has 100 g's in control, 3 g's off is easy to compensate for because the z-axis, it has control on the z-axis. But the helicopter has less than 3 g's of control. So a 3g error in anticipating what's going to happen to you is actually a real problem. And that's really why we had that crash. The big reason we had that crash that I showed you is because, yes, we did all the right things in terms of iterative LQR against our model and find a sequence of controls and so forth. But it was against a model that was so wrong that had errors in it like this. And if you are going to run your LQR optimization against models that are so wrong, you're just not going to get a good execution. Now, the interesting thing is that we did that experiment where we replayed the open loop controls from our pilot. And it flew roughly the same thing every time. Not at a precision level, but at a kind of high level gist, it was the same. So we concluded that maybe if we compare many trajectories, the error will be consistent. And indeed, that's what we saw. So as we had the pilot fly the same trajectory multiple times, and we looked at the error the model had along that trajectory, there's a pattern there. Once you run the alignment procedure, this is what you get. And you can see actually a very consistent pattern in the errors. So what this is showing is that these standard helicopter dynamics models we were using that come from textbooks, which are, of course, were designed for stationary flight regimes. That's what they had in mind, and the helicopter is doing acrobatic maneuvers, so obviously they're not going to be perfect, but they're highly imperfect, it turns out, but highly imperfect in a way that is very consistent as you execute the same maneuver over and over and over. You get the same errors happening along different rollouts. So what this means is that there's actually a decent amount of determinism to this process. And that maybe the only thing you need to do is say, well, maybe I cannot build a perfect helicopter model, but maybe what I can do is for this specific sequence of maneuvers at each time slice, I know how much I'm going to be off. I know that's pretty consistently the case. I can just insert that offset. And so essentially do a very simple model correction. That is, my acceleration at time t is off by this much. I'm going to just add it in such that now when I run my LQR against a new model, it anticipates those errors and knows they're going to be coming. So the reason you could expect is the case that our model does not very actually capture the airflow, but the airflow is still a physical thing that might be consistent as you do the same thing over and over. Same for actuator delays. We don't model them, but they might be consistently behaving the same way. And so in some sense, there are hidden variables that are not part of our state. But apparently those hidden variables, you can summarize the effect on the state we actually track in a very consistent way. So we set up a locally weighted regression. So instead of fitting the parameters on all the data, one set of parameters, we said, OK, at every time slice, we're going to use the data that's nearby. So we have a bunch of aligned trajectories from all the aligned trajectories, and you look at that time slice, look at nearby data, and fit your parameters specific to that time slice. Once we do that, here's what we can do. So here's the full setup. We have a helicopter. The helicopter has sensing on board, a microstrain 3DM GX1, which senses at 333 hertz. It has 3-axis accelerometer, 3-axis gyro, and 3-axis magnetometer. What do they do? 3-axis accelerometer measures acceleration. But actually, it's a little more subtle than that. Accelerometer measures acceleration relative to as if you were free falling. So if you're free falling, accelerometer measures 0 on all axes. But once you resist free falling in any way, accelerometer measures that. And so in some sense, let's say you're sitting on the ground, where you're resisting free falling by sitting on the ground, then you will know which direction gravity points. And so it's in some sense a way to know more about where gravity is pointing. Then the magnetometer, we all know about compasses. A compass will tell you which direction is north. Technically not exactly the north that we see on a map. The magnetic north is about, I believe, 15.5 degrees off from the north on the map, but we know for every location on Earth which direction the magnetic field is pointing. It's actually it's not just along the surface, it actually goes into the surface of Earth mostly. So most actually is a Z component. But you can actually then measure for your accelerometer how it's aligned relative to the magnetic field. What you don't have, let's say the magnetic field is pointing down, let's say that, then you don't know your rotation around the magnetic field axis, but you do essentially know 2 out of 3 degrees of freedom of orientation from the magnetometer. Then the gyros gives you angular rates around each of the 3 main axes. So a lot of orientation related measurements on board. We had a RPM sensor which measures the speed of the blades. And then a sonar which can measure distance from the ground. We also had cameras looking at the helicopter to know where it is. So once you have 2 cameras, you can triangulate. If you detect it in both camera views and know where the helicopter is in 3D space. And all that information gets fused into an extended Kalman filter, which is then outputting state information. Then, since we have a target trajectory, we can run receding horizon control against that target trajectory. We ran receding horizon control at 20 hertz. So every 1/20th of a second, we re-optimized our sequence of controls. More specifically, we ran iterative LQR. So we would essentially, on any given moment, we would run iterative LQR with a 2-second look ahead. So 40 time ticks into the future look ahead. Iterative LQR, a bunch of iterations, till we find our new sequence of feedback controllers, execute the first one, and repeat. Why 2 seconds look ahead is the furthest we could look ahead in the budget we had. If we tried to look ahead further, let's say 5 seconds or 10 seconds, iterative LQR would take too long, and then you have a lot of delay before you know what controls you want to send, and if you have a lot of delay, control becomes a lot harder. You want high frequency control to have better performance. So we could only look 2 seconds ahead. We did a bit of a calculation in simulation where we can slow down the dynamics of the helicopter. And so we found that looking 5 seconds ahead would have been ideal. Because after 5 seconds, against the model that we have, it would always have steered back onto track. After 2 seconds, it's not fully back onto the target. Once you're fully back onto the target, looking further ahead doesn't do anything for you. Because you assume you're on target, and you are on target in the future, so that's it. So ideally, we'd have looked 5 seconds ahead. We couldn't do it with compute budget at the time. What we could do, though, is we could do a pre-calculation. We would do interval QR ahead of time, find a sequence of cost-to-go functions, and so our 2-second look ahead was capped off by a quadratic cost-to-go function. And because we were close enough after 2 seconds to the target, that quadratic approximation of cost-to-go was good enough to essentially be as good as using the 5-second look ahead if you had more compute. Then the controls would go from a compute box into the back of the remote control for the helicopter, and if the pilot let them through he has a specific switch to let things through, then it would be sent to the helicopter, and then process repeats. So the full procedure would be something like this. We collect some sweeps, which is kind of you move the controls at different frequencies to get in some sense an understanding of the range of dynamics that's present in your helicopter. Then we learn a dynamics model from that. Then our pilot demonstrates the air show several times. We learn a target trajectory. We learn a dynamics model. Then we find optimal control policy for learn target and learn dynamics model. Autonomously fly the air show. And then we do yet another step that I haven't talked about yet, but essentially at this point it would actually work, but it would not be super precise, because the dynamics model was still from the initial data collection. So we'd actually get this data, in some sense do model-based RL, but in a very specific way, get the data from this execution, improve the dynamics model, and repeat. In about an hour time, we could learn to fly any new maneuver this way. So here's this in action now. So fully autonomous. Takeoff, inversion, hover. And so in this air show, we specifically chose to do all the things anybody had done before in the first few seconds. So we did hover, including inverted. We did here forward flight, split S, snap roll, and stall turn. And then we do new maneuvers that were never done before autonomously. So we did loops. If you are in good control of your helicopter, you can actually pirouette the tail around at the top when you're executing your loop. Stall turn, coming out tail first. Hurricane, which is fast backward flying circle. We went up to about 55 miles an hour with this helicopter. It's about this big, so it's a pretty high speed for this thing. Then inverted. Knife edge fall, and then stationary rolls and stationary flips. Now the stationary maneuvers actually are some of the hardest ones because you're maneuvering in the airflow that you just created. The faster you fly, the cleaner the air you get into, and in some sense the more predictable the behavior is that you're going to encounter from the air pushing on you. Tick-tock, and then at the end inverted hover. So might ask, did we actually fly what we wanted to fly? White helicopter is the target. Black helicopter is what we flew. I mean, what we think we flew, running the extended Kalman filter and smoother to estimate the state of the helicopter. And we see that indeed we're tracking the target very closely throughout all these dynamic maneuvers. In fact, we're as close to the target as the best results at the time for keeping a helicopter just in a single location hovering. So very, very high precision flight throughout any flight regime that we're considering here. Then I talked to you about auto rotation. The helicopter can still be controlled when the engine is dead. We decided to collect some data specifically for that to get, of course, the normal dynamics model wouldn't be that great in auto rotation because the normal dynamics model assumes you have an engine, and this thing does not have an engine that's functional. So we did a new data collection, started from new model, new demonstrations, but then indeed we're able to also get the helicopter to auto rotate. It's got kind of slightly bigger landing gear here because it's got a little bit of sideways speed at the end, and to make sure it doesn't tip if it kind of hits a bump on the grass. But so we did this probably close to 100 times, landing a helicopter autonomously with engine off, no problem. So pretty interesting how well that works. There's actually another thing interesting about auto rotation. There's another, maybe, curious if anybody knows. I told you can use auto rotation to safely land when your engine dies. Is there another reason you might want to use auto rotation, aside from for showing off?
The one reason I just thought of, which might be completely wrong, is if I'm trying to land a rover on Venus and my engine gets shot by the atmosphere, then
I like this idea. Imagine you're landing on Venus, which is like very difficult probably, and you arrive there with a helicopter that comes out of your rocket, but the engine gets shot, so you still have the same issue in some sense. Engine shot. Yeah.
Engines are really loud, right? So when you land them, you don't necessarily want to make them.
Yeah, so maybe you want to shut off your engine because you just want to quietly land. You don't want to disturb your neighbors or something. You say, okay, I'll come in auto rotation. Maybe that's quieter. It's actually very related. So actually, imagine your tail rotor gets lost. When you lose your tail rotor, the counter torque will make you spin, and it's pretty much impossible to control your helicopter at that point if you let it spin around. But if you shut off your engine, that counter torque is not there anymore. And so now your helicopter is actually stable, will not be counter torquing, and so if you lose your tail rotor, you'd actually deliberately shut off your engine, go into auto rotation to land. So it's a very interesting thing where you'd actually deliberately shut down, not just to be quieter, but as the only way to safely descend. Then a lot of people said hardest maneuver is chaos. So chaos was not in the original air show, but here it is. Helicopter doing chaos. So you're supposed to spin your tail around as fast as possible while flipping and rolling. And that's what it's doing here. And also while staying in place. You're not supposed to lose your position. And the beauty is that this is sustained. When we did it in open loop, I mean, it could do it for a couple seconds, you get the gist. But here it's actually staying in the same spot, pretty much the entire fuel tank. It can just keep going. Which we were, at that point, we essentially called it done because that was considered the hardest maneuver. But actually at the time I went to NIRPS, and this was 2007 or 2008, and I was talking with Jan LeCun, who is not only a deep learning person, but also has a lot of expertise in robotics. And showed him, I said, yeah, we can do every maneuver now, and I showed him the chaos. And he said, well, chaos, sure, but equally hard, tick-tock. Can you do tick-tock? So then we collected another one where we actually did essentially, again, indefinite, like full tank of fuel of just tick-tocking, showing that we can also sustain that. Chaos is probably harder than tick-tock, but I mean, both are considered very, very hard. And so here is the tick-tock in action, keeping the helicopter nicely in place. This is a very inefficient way to fly, by the way, because you are mostly vertical, so you're pushing the air in the wrong direction most of the time. Most efficient way to fly is upside down. The reason the most efficient way to fly is upside down is because as you push air down, you accelerate that air. And a kind of basic first principles calculation is that air goes at twice the speed after it's gone through the blades. That twice the speed air in normal flight would drag over the body of the helicopter, pushing the body down. But in inverted flight, you get just the regular speed air to go over the body, and then the 2x speed air doesn't go over the body. So what I thought is, in the last few minutes we have here, I think we have another 5 or 10 minutes, we will also have some course evaluations at the end, not forgetting about that. Go to kind of what happened behind the scenes, all of this. So this is the story of how it all works. Now let's see what actually we were doing. So first of all, helicopter pilots. Our helicopter pilot, Ben C., he had many jobs. So he had 2 startups and a regular job. So we did not have much access to flight experimentation. So he recommended his friend Antonio. His friend Antonio shows up. And okay, well, he seems like a pilot. That's great. First day Antonio's there, the most incredible thing happened I've ever seen, but it was not a good thing. But essentially, things were not carefully attached to our helicopter. Our helicopter went upside down. Something fell, hit the blade. When you hit a blade of a helicopter, these are very lightweight, strong but lightweight. But you hit it with something metal, you make a dent. You get an asymmetry. These blades are spinning around at super high speed. You have asymmetry in there. The helicopter just ripped itself apart. There was at least 100 pieces on the grass field spread out from just that one thing hitting the blade, asymmetry, and just starts ripping itself apart. Luckily, none of us got anything on our heads, but that was pretty worrisome. I'm like, okay, Ben's not available. Antonio got our helicopter ripped apart. Then the next thing that happens, we had a spare helicopter, and we say, okay, maybe we'll do some more experiments, we'll see. Antonio calls up his friend. He's like, hey, I'm having fun at Stanford flying some helicopters for some research project. You want to come out and fly some helicopters with us? And so somebody shows up, and this person shows up, pulls up their big truck, and they essentially pull out a few helicopters. They put one in front of us, like very close to us, and they just, I mean, once a year somebody dies from one of these helicopters, and just takes off right in front of us with almost no distance and starts doing essentially all the crazy maneuvers that we saw Sunday at the lake, but with like no distance from us. And we're like, okay, this guy knows how to fly a helicopter beyond anything we've seen except for that one video that inspired us, but not sure how responsible he is, because this is very dangerous. So we go back and we tell Andrew, we say, look, we lost the helicopter there. We're very sad about it. He said, no, don't worry. If you don't lose a helicopter every so often, it means you weren't pushing the boundaries enough. We say, well, we kind of lost it because just we didn't attach something properly. It's like, okay, yeah, well. And then this other pilot shows up and starts doing totally crazy things. Not sure what to do. Andrew's like, but it sounds like he's a good pilot. He's like, my intuition is that if you stand right behind the pilot, you're in a very safe spot. So maybe we can pay attention to being right behind the pilot when he comes. And so, but from there, we started working with the new pilot, Garrett, and he's just fantastic. Most responsible person we ever met. We just had no idea how much control he had over that helicopter the first time he showed up, and worked with him for many, many years from there. Then, when we started the project, we were trying to get this thing to work better. You saw the crash, and many things that didn't succeed, that didn't crash, but it was just like, okay, it just doesn't work, pilot takes control. We played with so many things. It was like, maybe the coordinate frame for our model should be attached to the helicopter. Maybe it should be attached to Earth. Like, little change, you think like, this little change is going to make the difference, and it maybe makes a difference, maybe not. You're trying to tease it apart and not clear. Then everybody telling us, oh, LQR, it's only the basic thing. You should do up-counted instead of discounted LQR, because up-counted cares more about the future, so it'll be more stable. We try that. They say, oh, the new thing in control is H-infinity control. You should try H-infinity control. Then they say, oh, well, the new thing, you need to do something with robust control. And like all this new, like, to something kind of mu synthesis was like the next big thing in control. Like, we try all those things. And they say, oh no, you should frequency shape your cost function. You should maybe put integrals on your errors. So you have some kind of PID style thing. And so we tried all those things that everybody was speaking very highly of as like, these are the things that matter. And we were like, nothing works better. And then we're like, isn't it the case that every one of those control methods ultimately returns a linear controller? So isn't it the case that as a consequence, if we just tweak the cost function in LQR, we can, by tweaking the cost function, also get essentially any linear controller back out. So it's really just a way to maybe more easily tweak the cost function, but it's much less intuitive to us, those other methods. So I guess we're really back to square one, which is just tweaking the cost function in LQR to see if we might find a better one that is more stable. Then we started realizing some of the things that happen when you go from simulation to real world. So real world pretty much always doesn't work as well as simulation. But can you do things to check if you have a high chance of success? So what we realize is that if you have a controller in simulation, and then in the simulator introduce random delays, so just random delays, you have like a 1/10 of a second delay. That makes it so much harder, and any controller you design that can handle that actually tends to work, much more likely work in the real world, even just for hover things at the time. Like, that was like our sanity check. Then we started thinking, control should be trivial if you have a high frequency control, so it should really be all about doing very fast sensing. Like if you have perfect sensing, you should be able to do a lot better than if you have lagged sensing or noisy sensing. We tested that in simulation, and we essentially compared doing rollouts when we put noise on the state, so it would be like things like wind gust effectively simulated, versus we put noise on the estimate of the state fed into our controller. And putting noise on the estimate of the state would be so much more harmful, because essentially you're controlling against the wrong thing. You think this is a state, you do the thing for the thing you think, but actually the reality is different. It's much more harmful than actually being pushed around in your actual state. Then we kind of started reading a lot of stuff on how can we get a better state estimate, and we ultimately found like there's this thing called a low-pass filter, the Chebby 5 low-pass filter, the magical Chebby 5 low-pass filter, which has less delay than any other low-pass filter. So because the helicopter is shaking so much, when you get your measurements from your inertial unit, there's so much noise on it, you need to low-pass it. And Chebby 5 is just this magical thing that gives you very low latency while smoothing things out. Then what we learned, which you can find in some places, but most people learn the hard way, is that when you have a filter like that, normally you look at it as like, okay, something like xt plus 1 is some linear combination of the previous axis. Then you're like, okay, that seems reasonable, and you set that up. It turns out you set it up that way, and you don't export more than, if you only export like 5 digits of precision, your filter is not the same filter. Essentially, the process here is that it turns out that the zeros of a polynomial are extremely sensitive to the coefficients of a polynomial. If you perturb the coefficients of a polynomial just a little bit, the zeros can shift a lot. And so that's effectively what's happening here. If you have a standard filter implementation, the way it behaves is determined by the zeros of the polynomial that filter encodes. And if you have low precision on the coefficients, all of a sudden your zeros are elsewhere, you might have something completely unstable. And then we realized that probably the problem is that our helicopter model is not precise enough. So we read books and books and books on helicopter modeling. People told us this is a helicopter Bible. This is what describes how helicopters work, like 500 pages on how helicopters work. We look at everything in there. And then only we conclude, the only things, like if you look at all the models, there's input variables and output variables. We already have those input and output variables. And since we learned the mapping between them, like there's nothing else we can do apparently. And we start realizing all those books are only for stationary flight regimes. None of them cover more aggressive flight regimes. And so that was like a lot of reading, a lot of interesting reading, but not very useful. Then we realized that to track the helicopter more reliably, we used to have a GPS. But when you flip it over, the GPS loses lock, and you need to wait like several seconds before you get the lock back. If you accelerate very fast, you might also lose lock again. So we started building our own GPS. And so we went to the Air Astro department. We said, we're going to build our own GPS. And they had a GPS lab. So the professor, the whole group, all they're doing is studying GPS systems. I'm like, okay, we want to build our own GPS. They say, wow, that's pretty wild. And we say, yeah, we're going to start with building a software receiver. We're going to log raw signals and build a software receiver and then build up from there. And they say, wow, that's a whole PhD thesis worth of work. And you're going to do that as an intermediate step for your research project. We're like, well, it seems like it should be feasible. So sure enough, a couple months later, we had what I guess was called a whole PhD thesis worth of work. We had it working. We're like, okay, that's good. We're on track. It was the first software-based GPS receiver, and it really worked. Then we're like, okay, to make this run faster, we need to deal with FPGAs. We started working with FPGAs. That was like a nightmare. It was so hard to program and debug. Ultimately, we got that working. Then like, now we need to do omnidirectional GPS, so multiple antennas, all running at the same time, and hand lock from one antenna to another antenna. And that's where we just completely got stuck. And maybe we could have seen this coming, but understanding like what the phase is when you go from one antenna to another antenna depends really on the geometry of the antenna, depends on so many factors of where the signals are coming from. You can't easily just have a phase difference between two antennas just based on measuring what the phase difference is. It depends on, because you measure from many different satellites and they'll have different phase differences with different satellites depending where they're positioned. And so at that point we just couldn't figure it out anymore. And after 1 year we're just like, okay, we have papers in GPS conferences on that, what we did, but we actually don't have a working system. Actually very frustrating. Very, very frustrating. 1 year of a lot of work, and it didn't come out the way we wanted to. In fact, at the time, like this company came by, some finance company, Goldman Sachs came by. They came to Stanford. It's like, they said, oh, we want to recruit. And I'm like, wow, that sounds better than trying to get this GPS to work. Maybe I should go talk to these guys and see what they're up to. And my friend who was, Morgan, was also working on the GPS project. He's like, yeah, my dad has a friend over in Connecticut, and he works at Goldman Sachs, and they live a good life. Maybe we should talk to them. Yeah, we talked to them, and it's like not that interesting. Okay, okay. Now back to trying to get this GPS to work. Then we're like, okay, why don't we just put cameras on the ground and look at the helicopter? And it's like, okay, but Andrew and Adam said, like, yeah, we did that 2 years ago. It didn't work. I'm like, okay. We tried this for a year. It also didn't work. We're going to at least give this a shot. We're going to at least try this again. I don't know what you tried then, but we'll try it now and see. And then 3 weeks later, we had a working system. It's like, OK, 1 year of effort versus 3 weeks, and we're good to go. It worked perfectly. Only catch was calibration took a long time. So we took the helicopter, we put the cameras, and we put the helicopter in the air, and then we collect an hour of data, an hour of calibration calculations, then we'll get out the calibration. Like, okay, how can we do this? Well, if we can keep the cameras on site, then we don't need to recalibrate, but that's kind of hard because it's just like a soccer field, and I mean, the soccer ball's flying around on other days, and how are we going to do that? So actually, our pilot was also a general contractor, so he knew how to build things. So our pilot built a contraption that you can snap onto fence posts. So whenever we show back up, we just snap it on, and our cameras were screwed in so tightly to that contraption that nothing could ever move, and we just like in 1 minute set it up and ready to go. So those are all things that are not really in the paper, but that made us a lot more efficient. Then we switched helicopters. It turns out the helicopter we had initially could generate about 1.5 to 2 Gs, but the Synergy N9 could generate 3 Gs. The more Gs you can generate, the more control you have over your system. But initially it was weighed down by the instrumentation board. Our instrumentation board was vibrating too much, so I put weights on it to make it vibrate less, can make it heavier, it doesn't shake as much. But then it's heavy, your helicopter's heavy, you lose like 1 G in the weight that you put on it. So we then actually, the big breakthrough, one of the big breakthroughs was we found this material called myoprene. You put that material on your helicopter and mount your instrumentation on that material. It just dampens out pretty much all the vibration, has near zero weight. All of a sudden we went back from 2G to 3G. Other things, oh yeah, Adam was just a genius in getting Linux to work. So Linux, the problem is, I mean, you have a lot of control, but most Linuxes, you just kind of install it. And it is what it is. And it'll run some processes in the background, and now you're stuck with those processes. He decided we're going to run Gentoo Linux. It's completely bare bones, like have nothing in there essentially. So nothing can run in the background. You need to compile it you need to compile it from scratch. You need to like go through all the details. But ultimately, once you did that, we could run things that we could essentially run a real-time operating system without having an official real-time operating system, because we were running nothing else on that system. And we didn't have to deal with any of the real-time programming that's really difficult to do as the interface or more complex, because we were just cleanly running just our code. Nothing could interrupt it. It was just our stuff running. That was it. Then the last thing that happened in the background is, oh yeah, when we were trying to get the auto rotation results, we had 3 days left for the paper deadline, and we go out and we tried to land, and it crashes. And so now we have a whole day. We have like nothing, no experiments that day. The next day, our pilot is repairing the helicopter. We have 1 day left. And so the little trick we played to make it all work, and the reason it crashed was because we lost track of the helicopter. Like essentially, because now when you're landing, you cover a much wider range, and one of the cameras had lost track of the helicopter. We didn't have the right state estimate. And so essentially the one day off was, for us, was all about installing warning signals. So our pilot, safety pilot, could know whether or not we were still tracking reliably and whether or not it should take back control. Once we did that, essentially we could land reliably every single time we didn't lose track of the helicopter. And when we did lose track on that day 3, then the pilot knew we lost track and could safely put it down and we could go again. And so a lot of things happening behind the scenes to make it all work. Yeah, and a lot of years of work. I think that's, yeah, if you're wondering, the one thing we never managed to control is, in principle, that helicopter can spin 2 times per second. So 720 degrees per second spinning. That's the place we never managed to control it. At that pirouetting speed, just our state estimation would just bail out, not really understand what's happening because it's spinning so fast. And you kind of need to measure things in the helicopter frame, which is spinning so fast that we kind of, that was the one limitation we were left with. And we said, okay, there's this one regime we can't do. We'll just leave it at that. Maybe in the future it'll be better sensing than we have today. Cool. That's all I had. I think, Murtaza, you're taking over for course evaluations. Thank you. You need a mic? You could use the box or...
Yeah, maybe that.